Okay, now we're going to determine the pH of a salt solution. We know how to calculate a Ka or Kb that might be missing for a conjugate acid-base pair. And so from that, we can determine the pH of almost any salt solution. Okay, so I have here, what is the pH of a 0.15 molar ethyl ammonium chloride solution? Now you'd say, well, how do I know if it's a weak base, a weak acid, or a salt? Well, you got to kind of look at the mixture here. Weak acids tend to be H something, or have an acid in some way. And they tend to be neutral compounds. And then weak bases are going to be amine type structures based off of ammonia, other than obviously our conjugates. So what we're looking at here is they've given me the Kb of a value, but when I look in the compound, I have the conjugate acid. I have an extra H plus on there. Remember, we always divide at an anion that comes from a strong acid or a cation that comes from a strong base. So here I have a Kb-Ka relationship. This is going to be what I'm interested in. So that chloride is a neutral ion. I don't really need it. It's a spectator ion, and it's not going to influence the pH in any way. So I'm going to write my equilibrium with water, and that's going to be C2H5 NH3 plus water. This being the conjugate acid of a base is going to act as an acid. Therefore, I'm going to donate this proton off and get the original base. And since it donated the proton, I'm going to get hydronium. Okay, well, I need the Ka for this. Ka is going to be equal to Kw divided by this value. So we did that on the last thing. That Ka is going to be 1.8 times 10 to the minus 11. Very, very weak acid. Okay, 1.8 times 10 to the minus 11. So now I go over here and I do my ice expression. I've got 0.15 minus x plus x plus x. Okay, I know the Ka. Ka is going to be equal to, and let's write this out, C2H5 NH2 concentration times the hydronium concentration divided by C2H5 NH3 plus, the original conjugate acid in the salt. Well, if I have 0.15 molar of this, I have 0.15 molar of each ion, since there's one ethyl ammonium ion per one chloride. So that is going to be that concentration. So I'm going to go over here and say, okay, x times x divided by 0.15 minus x is equal to 1.8 times 10 to the minus 11. We go through and assume this is negligible. Multiply 0.15 over and take the square root. So x equals the square root. 1.8 times 10 to the minus 11. Sorry, times 0.15. Take that square root and I'm going to get 1.6 times 10 to the minus 6. That's a very small value. Let's go ahead and do the 5% check, because really we should do that every time. 5%. We're going to take the amount of hydronium that would be produced, which is 1.6 times 10 to the minus 6, and divide it by what we assumed it was negligible relative to, which is 0.15. So we divide it by that. That gives me the percent dissociation times 100. That's going to be a very, very small value. That's 0.0011. Then we're good, way below 5%. Now I can go back and ask myself, okay, what is X? X is hydronium and the ethylamine concentration. Let's write those out. That's the hydronium concentration. It's also equal to the ethylamine concentration. Well, if it's a hydronium concentration, I can determine the pH, which is what I was trying to find originally in the problem, was the pH. So the pH now, I take minus log of 1.6 times 10 to the minus 6, and I'm going to get 5.80 as the pH. So that's the pH of this solution. Let's go over here and let's calculate the pH of a different solution. This time we have the potassium ion with the conjugate base of phenol. Okay? We know the Ka of phenol. We have 0.15 molar of this salt-type solution. Anytime you have a metal ion, break right at the metal ion. Say, okay, this comes from potassium hydroxide. Potassium ions come from strong base. Therefore, it is the neutral ion of a strong base. I can ignore it. It's a spectator ion, does not influence the pH in any way. This is going to be the conjugate base of a weak acid. You can see the conjugate acid-base pair there, H plus here, not here. Therefore, we can calculate the Kb here. Okay, so let's write our dissociation. We're going to have OC6H5 negative. I'm leaving the potassium off because it doesn't influence the pH in any way. Interacting with water. Well, this is a conjugate base, so it's going to receive a proton. So we're going to make HOC6H5. That's going to be our phenol, and then we're going to have hydroxide as a result. So we're forcing water to be the proton donor. It donates the proton, leaves hydroxide behind. We have 0.15 molar minus X plus X plus X. I need the Kb. The Kb I can get from the Ka because Ka times Kb equals Kw. So I plug this in and divide it into 1.0 times 10 to the minus 14, and I'll get a Kb equal to 6.3 times 10 to the minus 5. Well, now I can solve this. I've got my equilibrium, which is 0.15 minus X, and X, and X. Kb is going to be equal to, let's write out the full expression here. Kb is going to be equal to phenol, HOC6H5, times hydroxide, divided by OC6H5 negative. Well, that's X times X over 0.15 minus X. All of that equals 6.3 times 10 to the minus 5. I'm going to assume this is negligible. That will keep us from doing the quadratic formula. Bring the 0.15 over. So X equals the square root of 6.3 times 10 to the minus 5 times 0.15. Do that square root, and we're going to get 3.1 times 10 to the minus 3 as X. Well, we need to prove this is a valid value of X. It's going to be the 5% check. So we're going to go through and say, okay, let's calculate this. 3.1 times 10 to the minus 3 relative to an original concentration of 0.15 times 100. And we will get, as a result, 2.0%. We're valid at 2.0%. Now let's go back and ask ourselves, what is X? Well, X is going to be the hydroxide concentration, and it's also the phenol concentration. Since X is a hydroxide concentration, we're going to get the POH. POH from 3.1 times 10 to the minus 3 is 2.51. Subtract that from 14 and we'll have the resulting pH, which is 11.49. So determining the pH and POH of salts is going to require working with a conjugate acid or conjugate base. Be aware, the value of Ka and Kb for those are not going to be found in our typical tables of Kas and Kbs.